Hello, Chemistry 30, and welcome to your new unit, your last unit in Chem 30, which is on organic chemistry. Just kind of some quick talking about things before we get started. So organic chemistry is a whole branch of chemistry. In fact, in university, if you go into chemistry, or if you're not and you're just going to, let's say, something like medicine, you will have to take organic chemistry. It's one of the tougher classes you'll end up taking in university. And then that goes into, biochem and that kind of stuff as well. But organic chemistry is all about looking at chemicals that contain carbon. And specifically like carbon connected to other carbons and stuff. We're going to talk about what is organic and what isn't organic. But this is, like I said, a whole branch of chemistry, particularly important to, of course, living things, but it's all throughout life. I mean, organic chemistry brings us things like plastics and artificial flavors and tissues and drugs and so many different things. It's all organic chemistry. So this is a large kind of body of chemistry that has to do with very practical type of chemistry. So this unit is going to feel a lot different than other units we've done. No math. We have zero math in organic chemistry at all. So for some of you, that'll be absolutely fantastic. For others, maybe that's your strength, but there is no math here. What it is a lot of our work is going to be learning about a naming and drawing system. So how to name different organic compounds. It kind of ties into this whole nomenclature, so way of naming that you have to learn that differentiates very similar compounds one from the other. Because the neat thing about organic chemistry is compounds that are incredibly similar end up being completely different in their properties in, for example, like the human body, which is very important as we go into organic chemistry. So we have specific names for different compounds, and you're going to learn that system. And that's what our first week and a bit is going to be focused on, is actually just learning the system of naming. Normally, we do this unit in about 2 weeks in the normal school year. So we're left with about 2 weeks here as well. We are going to cut out a few things here and there that I just feel like aren't very applicable going into university and we don't need. But it's going to be similar in terms of what you get here as what you would have gotten in a normal organic chemistry unit in school. So, organic chemistry is a study of most carbon-containing compounds. All organic compounds contain carbon atoms, but not all carbon-containing compounds are classified as organic. So things that contain carbon, but that are not classified as organic, so they would be the opposite, which is inorganic, is carbonates, cyanides, carbides, and then carbon oxides. So carbonates means that I have, of course, the CO3 2- ion in it. That is not classified as organic. Cyanides means the Cn-, again, not classified as organic. And then carbides is where I have just a carbide ion, and I'm honestly forgetting what the charge is for a carbide ion. I think it's 2-, but I'm not sure. And then I have, so metal carbides, if I had like tungsten carbide, for example, okay, that would be then, again, a carbide. So it's where carbon is acting as an anion. So you're seeing a trend. When I have a very small carbon anion, right, then that's not organic. And then the last thing is when I have oxides of carbon, so carbon monoxide, carbon dioxide, those are also not classified as organic compounds. So why do we care? Well, carbon is found in nature both as an element and in its combined form. Although carbon ranks 17th in abundance by mass among the elements in the Earth's crust, it is exceedingly important because it is found in all living matter. Why is carbon so special? Well, it can form 4 covalent bonds, right? So it has 4 bonding electrons when you draw the electron dot diagram for carbon, which I'll do right over here. 1, 2, 3, 4. So it's got 4 spots to form covalent bonds. It can also form double and triple bonds. Carbon forms very strong bonds with other carbons, which allows it to form these very long chains and rings, etc. It's amazing how many carbons we can get connected in incredibly different ways. It's like super incredible 3D Lego. Lego is 3D as well, but it's amazing how it can connect to different carbons. And it is possible for the same number of atoms of carbon and other elements to have more than one arrangement or isomer. You learned about isomers in Chem 20, and maybe that was a difficult concept for you. What's neat is that in Chem 30, in learning how to do naming, nomenclature, isomers now become incredibly easy because you know it's an isomer if it has a different name, and you're going to learn the system for naming. In fact, today you're going to learn how to name alkanes. Okay, and I'm probably going to do that kind of as a separate video just in terms of my later use. I'm going to stop this video, start the next one in just a moment here, but you're going to learn how to name alkanes, which is carbons that all have single bonds connected to each other. So that's some properties about carbon that make them very special. So carbon can be found in different forms in nature. I don't actually like that coal is here. I don't consider that what's called an allotrope of carbon. So when I talk about allotropes, it's different ways that the element of carbon can actually like appear in nature. But carbon can be in graphite form. So graphite is the same thing that you use in your pencil. It's interesting because in graphite form, carbons are all connected kind of in this hexagon arrangement that repeats over and over and over again. And then that goes into sheets. So you can see that I have these hexagon kind of patterned sheets that are connected. And that's what allows graphite in pencils to write, is that as you're writing, you're kind of laying out these sheets of graphite down in pieces. Diamond is carbon connected in a tetrahedral arrangement over and over and over again, which gives it incredible strength. I mean, diamond is one of the hardest substances on Earth because of this tetrahedral arrangement in this allotrope of carbon. And kind of amazing, this is a little sample, but you could build this with a model kit where you have tetrahedrals building on tetrahedrals over and over and over again to show you diamond. And it's really neat to see how that actually all just kind of connects. But that's diamond. And then this is kind of a really neat buckyballs or Buckminsterfullerenes, which is actually carbons connected in both pentagons and hexagons. And it looks essentially like a soccer ball pattern. And this is another allotrope of carbon, so another form that you can find elemental carbon in. And we take these fullerenes and then we connect it with carbon nanotubes and stuff. And it's kind of a whole neat area of technology of building these cool shapes out of carbon and then finding applications for it. Anyways, moving forward, we are going to start by looking at things that contain just carbon and hydrogen, in other words, hydrocarbons. And then after that, we're going to get into what we call hydrocarbon derivatives, where we throw in halogens, right? Carbon, fluorine, bromine, iodine, or we, did I say carbon or chlorine? I meant chlorine. Or we throw in oxygen in the form of alcohols, and then we go into carboxylic acids and esters. Okay, so we're going to go into different derivatives, but for right now, we're starting with just sticking with carbon and hydrogen together. So we have a few different ways that we can actually draw different structures. This is a full structural diagram right here. So this is showing every single bond, okay, between carbon and hydrogen, and then also the carbon-carbon bonds. Most of the time what we're going to do is actually condensed structural formulas or structural diagrams where I'm showing the carbon to carbon bonds with these lines, but I'm not showing the carbon to hydrogen bonds. Now, don't get confused about the fact that this line goes to the H2. It actually is like going to the carbon, okay, but it's hard to write that in a way that makes sense and have it all in one line. Okay, so instead, we just kind of draw it where it's, CH3 and then a line to CH2 and then a line to CH2. And those lines represent carbon to carbon bonds. Then we also have line structural formulas, of which form this is the most popular. Each one of these vertices represents where a carbon is. And again, I'm drawing the lines that connect carbons. Now, what isn't shown here at all is the hydrogens. So we have to figure out the hydrogens after the fact if we're finding the formula for this, by realizing that because carbon always has 4 bonds, that this carbon would have 3 hydrogens, this one would have 2, this one would have 2, this one would have 2, whoa, messed up there, and this one would have 3. So this would end up being C5, 1, 2, 3, 4, 5, H12, 12 hydrogens here that I have in total. But that is, getting ahead of myself, that is a condensed structural diagram, a line structural diagram, where I'm just showing the connections between carbons, and each vertices of this line represents a carbon that is then connected by these lines. This is a very popular way of drawing organic compounds, and it's popular because it's very quick and easy to do, right? I just have to draw the lines and I'm done. You're going to get good at drawing those as time goes on. Most of our work, though, is going to be in this condensed structural formula, most of it looking like what you see on the left right here. Sometimes for very huge compounds, we're actually going to put CH2 and then how many we have kind of in brackets here. So this is the same compound, but these 3A CH2s I can write as in brackets CH2 and that just shows that, hey, I got this really long chain. Now you might think this is silly for something with only 5 carbons, but imagine something like C50 or whatever. If I had something like C50 102 H's, I mean, drawing that would just be absolutely insane as a normal condensed, but I can draw this simply as CH3 line CH2 bracket 48 and then a CH3, and hooray! I end up then having my full condensed structural formula for a massive, massive long hydrocarbon chain. All right, so 3 different kind of diagrams we're going to deal with: our normal full structural diagram, our line diagram or structural formula, and then also our condensed structural formula. Okay, so that's it for general organic talk in diagrams. Next, we're going to talk about alkanes.